There's something about the Pinwheel Galaxy that defies explanation. Floating 25 million light-years away, this cosmic whirlpool of stars, officially known as Messier 101, is one of the most breathtaking sights in the night sky. But beyond its dazzling spiral arms and glittering starlight lies a mystery that has left astronomers scratching their heads. This isn't just another pretty face in the cosmos. It's a hotbed of bizarre phenomena, from unexplained energy bursts to celestial objects behaving in ways that shouldn't be possible. What if I told you that some of these mysteries could rewrite our understanding of physics itself? Picture this: a galaxy so vast it could swallow our Milky Way whole, yet delicate enough to resemble a child's pinwheel spinning in the cosmic breeze. But don't let its beauty fool you. Nestled within its swirling arms are secrets that challenge everything we think we know about the universe. Supermassive black holes that vanish without a trace, stars that flicker like cosmic ghosts, and regions of space where time itself seems to warp. These aren't just anomalies. They're clues whispering to us from across the void, begging us to dig deeper. And that's exactly what we're going to do today, because this isn't just a tour of strange sights, it's a journey into the unknown. Over the next 30 discoveries, we'll unravel the enigmas of the Pinwheel Galaxy piece by piece. Some will make you question reality, others might send a chill down your spine. But one thing's for certain: by the time we're done, you'll never look at the night sky the same way again. So buckle up. We're about to dive into a cosmic mystery that's as thrilling as it is unexplainable. The first mystery of the Pinwheel Galaxy isn't about something strange that's there. It's about something that isn't. At the heart of most spiral galaxies, including our own Milky Way, lurks a supermassive black hole, an invisible monster with gravity so strong it bends space and time. These cosmic behemoths are the anchors of their galaxies, influencing how stars move and even how galaxies evolve. But when astronomers trained their telescopes on the pinwheel's core, they found nothing. Just an eerie quiet where a gravitational giant should be. So where did it go? One possibility is that it's hiding behind thick clouds of dust and gas camouflaged from our view. But even then, we'd expect to detect the faint ripples of its influence, telltale signs like stars orbiting at impossible speeds or bursts of X-rays as matter spirals into oblivion. Yet the pinwheel's center remains stubbornly silent, as if the black hole simply packed up and left. Then there's the wilder theory: what if it was kicked out? Galactic collisions can send supermassive black holes careening through space like billiard balls, flung by gravitational forces too immense to imagine. If another galaxy once grazed the pinwheel, the resulting chaos might have ejected its central black hole entirely, leaving behind a ghostly void. But here's what really boggles scientists' minds: if the black hole is truly gone, how is the pinwheel still so perfectly structured? Without that gravitational anchor, its elegant spiral arms should have unraveled long ago. Yet there it spins, defying expectations, as if nature itself is taunting us with a question we can't yet answer. What other rules of the cosmos might this galaxy be breaking? The hunt for answers is just beginning. While the Pinwheel Galaxy's missing black hole is one cosmic puzzle, its scattered ultraluminous X-ray sources, or ULCs, are another enigma entirely. These celestial powerhouses blast out X-rays with a brightness that defies logic, shining millions of times brighter than our sun. Normally, X-rays this intense come from matter spiraling into supermassive black holes, but here's the twist: ULXs aren't anchored in galactic cores. They're scattered like cosmic landmines across the pinwheel's spiral arms, far from where such extreme energy should originate. So what could possibly fuel these dazzling monsters? One leading theory points to intermediate mass black holes, cosmic middleweights bridging the gap between star-sized black holes and their supermassive cousins. These elusive objects, long theorized but rarely spotted, could explain the ULC's ferocious energy output. Imagine a black hole weighing 1,000 suns, devouring entire stars in fits of gravitational fury. Yet even this idea raises questions. How did so many of these mid-sized beasts end up scattered across a single galaxy? Then there's the wild card, exotic stellar objects defying known physics. Some scientists suggest ULXs might be magnetar neutron stars with magnetic fields so powerful they distort the very fabric of space. Picture a dying star so dense a teaspoon of it would weigh 1 billion tons, spinning at dizzying speeds while magnetic forces twist its surface into eruptions of X-rays. Others propose microquasars, tiny versions of galaxy-spewing jets, where stellar black holes gulp down gas and spit out energy in concentrated beams. But here's the real kicker: some ULXs flicker. Unlike the steady glow of supermassive black holes, these sources pulse and dim unpredictably, as if something out there is toggling the cosmic light switch. This behavior throws another wrench into our theories, suggesting environments so extreme they warp the very rules of energy emission. What makes the Pinwheel's ULXs especially baffling is their numbers. Most galaxies host a handful of these extreme objects at most, yet this galaxy is practically studded with them, like a cosmic carnival lit by too many X-ray bonfires. Are we witnessing a freak cosmic accident, or a glimpse of physics operating under rules we've yet to uncover? Every flicker, every burst from these radiant anomalies is a whisper from the universe, daring us to rethink what's possible. And with each new observation, the Pinwheel Galaxy proves it's not just beautiful, it's a laboratory for the impossible. The Pinwheel Galaxy has a red supergiant problem, and no, it's not about their color. These colossal stars, the bloated final act of massive stellar lives, should be littering the galaxy's spiral arms like cosmic campfires, yet when astronomers counted them, the numbers didn't add up. Based on everything we know about star formation, the pinwheel should be teeming with hundreds of these crimson giants. Instead, it's oddly empty, as if someone quietly turned off a faucet that should have been pouring them out. This isn't just a head-scratcher for star enthusiasts. Red supergiants are cosmic cornerstones, the factories where elements like carbon, oxygen, and iron are forged before being blasted into space in supernova explosions. Their absence throws a wrench into our models of stellar evolution, the very playbook we use to understand how stars live and die. It's like opening a textbook on trees and realizing an entire forest is missing. So what's stealing the Pinwheel supergiants? One clue lies in the galaxy's unusual star-forming history. Unlike the Milky Way, where star birth ebbs and flows, the Pinwheel seems to have had sporadic, explosive bursts of stellar creation. Imagine a fireworks show with long pauses between sudden, violent eruptions. During these frenzied periods, massive stars may have burned too hot and fast, skipping the supergiant phase entirely and collapsing straight into black holes or neutron stars. Then there's the metallicity mystery. Stars in the pinwheel have lower concentrations of heavy elements, what astronomers call metals, compared to our galactic neighborhood. Metal content affects how stars age, like a cosmic diet altering their lifespan. With fewer metals, massive stars might shed their outer layers too efficiently, shrinking prematurely into compact objects before ever puffing into supergiants. It's the stellar equivalent of a teenager never hitting a growth spurt, but the wildest possibility: the missing supergiants might not be missing at all. Some could be hiding in plain sight, shrouded by thick veils of dust ejected during their turbulent lives. Or even stranger, they might be evolving in ways we've never seen, defying the standard stellar playbook entirely. Every time we think we've cracked the code of how stars behave, the Pinwheel Galaxy throws us another curveball, reminding us that the universe is far weirder than our textbooks dare to suggest. Among the Pinwheel Galaxy's many oddities, few are as dramatic as its hypervelocity runaway stars, cosmic outcasts hurtling through space at speeds that defy gravity's grip. These stellar fugitives don't just drift away, they're launched like bullets from the galaxy's disk, racing at thousands of kilometers per second, fast enough to cross entire star systems in the blink of a cosmic eye. And their existence forces us to ask, what kind of celestial slingshot could possibly fling a star with such violence? The prime suspect, supernovas. When a massive star explodes in a cataclysmic blast, the sheer force can eject its companion star like a pebble from a slingshot. Picture a binary pair locked in orbit. One star dies in a fiery supernova, and the survivor, suddenly freed from its gravitational tether, rockets into the void at unimaginable speeds. Astronomers call this a supernova kick, and it's one of nature's most extreme eviction notices. But here's the catch. While supernovas explain some runaways, the pinwheel's fastest stars are moving too fast, as if something even more powerful gave them an extra push. That's where the galaxy's missing black hole comes back into play. Though its central supermassive black hole may be absent, smaller, rogue black holes could still lurk in the pinwheel's spiral arms. If a star wandered too close to one of these invisible predators, the black hole's gravity could fling it away in a cosmic game of pinball, a process known as the Hill's mechanism. The math checks out. A close encounter with a black hole could accelerate a star to hypervelocity speeds, turning it into a galactic exile. But the implications go beyond stellar fireworks. Runaway stars are cosmic breadcrumbs hinting at unseen forces shaping their home galaxy. Their trajectories map invisible gravitational hazards, black holes, dense star clusters, or even dark matter anomalies. And when these speedsters finally escape their galaxy, they become intergalactic voyagers carrying the pinwheel's composition into the emptiness between galaxies. Some might even seed future star formation in entirely new corners of the universe. Yet the pinwheel's runaway stars leave behind their own mystery. Unlike other galaxies where hypervelocity stars are rare and scattered, the pinwheel seems to produce them in clusters, as if entire groups of stars were ejected in tandem. Could a single, catastrophic event like a close encounter with another galaxy have sent shockwaves through the pinwheel, dislodging whole stellar neighborhoods at once? Or is there something fundamentally different about how this galaxy handles stellar traffic? Every runaway star is a message in a bottle, carrying clues about the violent, invisible forces that sculpt our universe, and the Pinwheel Galaxy seems determined to write those messages in bold. The Pinwheel Galaxy isn't just forming stars, it's practically hosting a cosmic baby boom. While most galaxies produce stars at a leisurely pace, this spiral wonder cranks them out like an overclocked stellar factory, with regions like NGC 5461 and NGC 5462 shining brighter and birthing stars faster than anywhere else in the local universe. These aren't just ordinary nurseries, they're sprawling, turbulent cauldrons where gas collapses into new suns at rates that leave astronomers bewildered. What's fueling this celestial fertility? Start with the galaxy's staggering gas reserves. The pinwheel is drowning in hydrogen, the raw material for star birth, with clouds so dense and widespread they outmatch similar galaxies by a wide margin. Picture a vast interstellar ocean, its waves not of water but of cold molecular gas, primed to collapse under gravity's pull. But gas alone doesn't explain the frenzy. Something had to stir the pot, and the leading suspect is a brutal cosmic collision in the pinwheel's past. Evidence hides in the galaxy's lopsided structure. One side of its spiral arms appears stretched and warped, like taffy pulled by an invisible hand. Computer simulations suggest a smaller galaxy once sideswiped the pinwheel, injecting chaos into its orderly rotation. The gravitational shockwaves would have compressed gas clouds to critical densities, igniting chain reactions of star formation. It's the galactic equivalent of shaking a soda can before opening it, except here, the fizz is a fireworks show of newborn stars. Yet even this explanation has cracks. The pinwheel's star-forming regions don't just outproduce others, they break established rules of stellar physics. In areas like NGC 5462, Massive stars form in clusters so tight they defy predictions about how such crowded environments should behave. Normally, fierce radiation from the biggest stars would blow away nearby gas, stifling further star birth. But here, new suns keep emerging in the storm's eye, as if the galaxy found a loophole in the laws of astrophysics. Then there's the metallicity twist. Younger stars in these regions show unusually high concentrations of heavy elements, the cosmic byproducts of previous stellar generations. This suggests the pinwheel isn't just forming stars rapidly, it's recycling its materials with freakish efficiency, like a cosmic thrift shop turning old star stuff into new celestial bodies faster than should be possible. Could dark matter play a role? Some theorists propose that an uneven distribution of this invisible substance might be funneling gas into the galaxy's busiest regions, supercharging star formation like hidden scaffolding guiding construction. Others point to rogue magnetic fields twisting through the pinwheel's arms and sculpting gas into dense knots ripe for collapse. What's clear is that this galaxy operates on a different rhythm. While others fade into quiet middle age, the pinwheel burns bright with youthful energy, challenging our understanding of how galaxies evolve. Every blazing star cluster, every gnarled nebula in its arms is a testament to nature's ability to rewrite its own rules, and a reminder that the universe always keeps a few surprises up its sleeve. The Pinwheel Galaxy doesn't just puzzle us with what we can see, it's what we can't see that might be its most baffling secret. Every galaxy is thought to be cocooned in a sprawling halo of dark matter, an invisible gravitational scaffold that holds its stars together. But when scientists mapped the pinwheel's dark matter, the numbers came out all wrong. Instead of the smooth, evenly distributed cloud predicted by theory, this galaxy's dark matter seems patchy, uneven, and in some regions barely there at all. It's like finding a house standing upright with half its foundation missing. So why does this matter? Dark matter isn't just cosmic decoration. It's the glue that keeps galaxies from flying apart. Without enough of it, a galaxy's outer stars should be drifting away like leaves in the wind. Yet the pinwheel's spiral arms spin gracefully, its stars orbiting as if anchored by something unseen. The mismatch suggests one of two jaw-dropping possibilities. Either our models of dark matter are fundamentally flawed, or this galaxy has found a way to defy them entirely. One clue lies in the pinwheel's turbulent past. Computer simulations show that galactic collisions can strip away dark matter, scattering it like crumbs from a broken loaf. If the pinwheel endured a violent encounter billions of years ago, the gravitational chaos might have redistributed its dark matter unevenly, leaving gaps where we'd expect it to be thickest. But here's the catch: even in those simulations, galaxies rarely end up as lopsided as the pinwheel appears. Then there's the radical alternative. What if dark matter isn't what we think it is? Most theories describe it as a slow-moving, cold substance that clumps predictably, but the pinwheel's uneven halo fuels speculation about warm, dark matter, particles moving fast enough to resist clustering. Imagine a swarm of fireflies instead of a snowbank. Their light flickers unpredictably, never settling into a steady shape. If true, it could rewrite the rules of how galaxies form, suggesting the cosmos is far more dynamic and messy than our tidy models assume. The real shocker: some patches of the pinwheel's outer edges seem to orbit faster than they should, as if tugged by invisible concentrations of mass we can't account for. This isn't just missing dark matter, it's dark matter behaving in ways that shouldn't be possible. Could there be rogue clumps of it drifting like invisible icebergs? Or does this galaxy harbor hidden structures, cosmic shortcuts, or warps in space-time that distort our measurements? Every anomaly in the pinwheel's dark matter halo is a crack in the foundation of modern astrophysics. If this galaxy can flout the rules so brazenly, what else have we gotten wrong? The answers might not just reshape our understanding of the pinwheel, they could redefine the invisible skeleton of the universe itself. The Pinwheel Galaxy's spiral arms should be a masterpiece of cosmic symmetry, sweeping, graceful curves that unwind from its core like ribbons in the wind. But peer closer and the illusion shatters. Some of these arms are fractured, their stellar trails broken into jagged segments, as if the galaxy itself is a puzzle missing crucial pieces. These phantom arms don't just fade, they stop abruptly, then restart elsewhere like a highway torn apart by an invisible quake. And the question haunting astronomers isn't just why, it's how a galaxy can look so perfectly imperfect. Gravity is the usual suspect. In most galaxies, spiral arms are density waves, cosmic traffic jams where stars and gas pile up as they orbit, creating the illusion of solid structures. But the pinwheel's disjointed arms suggest something disrupted this delicate dance. One theory points to a close encounter with another galaxy, a gravitational bully that sideswiped the pinwheel and sent shockwaves rippling through its disk. Picture throwing a rock into a pond. The initial splash distorts the water's surface, but the ripples that follow can bend and break in unpredictable ways. If a smaller galaxy grazed the pinwheel billions of years ago, the gravitational aftershocks might still be echoing, leaving these fractured arms in their wake. Then there's the darker possibility, an unseen companion. Astronomers have found galaxies hiding cosmic hitchhikers before, dim, dwarf galaxies made mostly of dark matter, orbiting like ghosts just beyond the visible edge. These stealthy neighbors could tug on the pinwheel's arms without leaving obvious traces, their gravity snipping stellar streams like invisible scissors. Some researchers are scouring the galaxy's outskirts for any flicker of movement, any subtle warp in the starlight that might betray a hidden culprit. But the weirdest twist, some fragmented arms glow hotter and younger than their surroundings, as if the disruption triggered star formation rather than stifling it. Normally, gravitational chaos scatters gas, making it harder for stars to birth. Yet here, the torn edges of these phantom arms are studded with brilliant blue clusters, stellar newborns blazing where destruction should reign. It's like finding a garden flourishing in the cracks of an earthquake. Could the pinwheel be teaching us that spiral arms aren't just decorative, that their breaks and kinks might actually forge the conditions for new stars? Every gap in these arms is a challenge to our assumptions, a reminder that even the most beautiful galaxies hide chaos beneath their shimmering surfaces. And until we solve the riddle of these phantom spirals, we're left staring at a cosmic fingerprint, one that might belong to forces we've yet to name. Tucked within the Pinwheel Galaxy's ancient spiral arms, there's a stellar rebellion underway, scattered blue stars burning too hot, too bright, and too young for their surroundings. These aren't just ordinary stars, they're cosmic rule breakers, shining defiantly in neighborhoods where theory says they shouldn't exist. Astronomers call them blue outliers, and their very existence throws a wrench into our understanding of how stars are born, live, and die. Picture a retirement community where every resident is silver-haired except for a few vibrant 20-somethings lounging on the porches. That's the pinwheel's paradox. Most stars in these regions are aging giants, their golden light hinting at billions of years of steady burning. But the blue outliers blaze with the vigor of youth, their ultraviolet glow betraying a recent birth. The problem, there's no trace of the stellar nurseries that should have spawned them. It's like finding a newborn in a ghost town long abandoned by its parents. So how did these stars cheat time? One clue lies in their isolation. Unlike typical young stars which cluster like grapes on a vine, many blue outliers drift alone, far from the gas-rich regions where new stars usually form. This suggests they might be galactic nomad stars born elsewhere and flung into these aging neighborhoods by gravitational chaos. Imagine a massive star cluster near the pinwheel's core, where overcrowding leads to violent gravitational tug-of-wars. A close encounter with a black hole or a runaway collision could eject stars at incredible speeds, sending them sailing across the galaxy like cosmic outcasts. By the time they settle in these quieter corners, their birthplace has faded from view, leaving only the mystery of their youth. Then there's the delayed formation theory. Some astronomers propose that pockets of gas in the pinwheel might have remained dormant for eons, untouched by the usual triggers of star birth, until something jolted them awake. A passing shockwave from a supernova, the gravitational nudge of a dark matter clump, or even the ripple of a long-ago galactic collision could have compressed these sleeping gas clouds, igniting star formation billions of years after their surroundings faded into old age. It's the cosmic equivalent of a time capsule bursting open millennia too late. But the most tantalizing explanation challenges the very timeline of stellar evolution. What if these stars aren't young at all? Some models suggest that under rare conditions, stars might siphon material from a companion or interstellar gas, reviving their outer layers and masquerading as newborns. Like a 70-year-old marathoner with the stamina of an athlete half their age, these rejuvenated stars could be older than they appear, their blue glow a cosmic disguise. The pinwheel's blue outliers aren't just celestial oddities, they're stress-testing our models of galactic history. Every one of these rebellious stars forces us to ask, have we misunderstood how galaxies evolve, or is the pinwheel playing by a different set of rules entirely? In a universe where time is supposed to march forward predictably, these stars are the wild cards, reminding us that the cosmos still has a few tricks up its sleeve. Beneath the Pinwheel Galaxy's shimmering spiral arms lies an invisible enigma, a faint but persistent gamma-ray glow with no identifiable source. Unlike the brilliant bursts of energy from supernova or pulsars, this radiation blankets vast regions like a cosmic fog, defying every attempt to trace its origin. It's not just mysterious, it's impossible by conventional astrophysics standards. Gamma rays are the universe's most energetic light, born from extreme violence colliding stars, annihilating antimatter, or the crushing gravity of black holes. So why is the pinwheel radiating them so quietly, so everywhere? One spine-tingling hypothesis points to dark matter, the universe's most elusive substance. Theorists suggest that if dark matter particles collide and annihilate, they could release gamma rays as a byproduct. The pinwheel's diffuse glow might be the ghostly signature of this invisible process, a shadow dance of particles we've never directly detected. Imagine lighting a match in a pitch-black room, only to realize the glow isn't from the flame, it's from the walls themselves. If true, this could be our first glimpse of dark matter's hidden interactions, a Rosetta Stone for decoding the universe's missing mass. But not all astronomers are convinced. Skeptics argue the glow could stem from thousands of unresolved pulsars, the spinning corpses of dead stars, each too faint to detect individually but collectively flooding the galaxy with gamma rays. Pulsars are nature's lighthouses, beaming radiation as they rotate, and the pinwheel star-forming frenzy would have seeded plenty of these stellar remnants. Yet even this explanation falters. The glow's distribution is too smooth, too even. Pulsars cluster in predictable ways like street lamps along a highway, but the pinwheel's gamma rays are more like mist, pervasive and untraceable. Then there's the wild card, cosmic rays colliding with interstellar gas. When high-energy particles slam into hydrogen clouds, they can spark gamma-ray emission. But here's the catch: the pinwheel's gas density doesn't fully account for the glow's intensity. It's like trying to explain a bonfire with a handful of matches. The most unsettling possibility: we're seeing a blend of all three plus something entirely new. Perhaps the pinwheel's unique structure, its turbulent history, or even unseen physics is amplifying these signals in ways we can't yet model. Every photon of this unexplained glow is a question mark, a silent challenge to our understanding of how energy weaves through the cosmos. And until we crack its code, the pinwheel's gamma-ray whisper remains one of its most tantalizing secrets. Galaxies like the pinwheel should be dripping with globular clusters, ancient, dense balls of stars that orbit like cosmic bees around a hive. Our Milky Way boasts over 150 of these glittering relics, each a fossilized snapshot of the universe's fiery youth. Yet when astronomers counted the pinwheel's globulars, they came up shockingly short. Where most galaxies its size shimmer with these stellar time capsules, the pinwheel clings to barely 24, as if someone swept through and plucked them away. This isn't just a case of cosmic forgetfulness. Globular clusters are galactic history books encoding clues about a galaxy's earliest days. Their scarcity in the pinwheel suggests one of two unsettling possibilities. Either this galaxy was born under unusual conditions, starved of the raw materials needed to form them, or it suffered a violent encounter that ripped them away. Let's start with the birth defect theory. Globular clusters form in the chaotic aftermath of galaxy formation, when vast clouds of gas collapse under gravity's grip. If the pinwheel emerged from a gas pool unusually low in heavy elements, its protoclusters might have fizzled before they could ignite. Picture trying to build a bonfire with damp wood. The sparks catch, but the flames never take hold. Supporting this, some of the pinwheel's remaining globulars are chemically peculiar, with metal contents lower than typical clusters, hinting at a starved start. But the more dramatic explanation involves cosmic theft. Galaxies don't evolve in isolation. They're gangsters in a gravitational underworld, stealing stars and clusters from one another during close encounters. The pinwheel's distorted spiral arms hint at past collisions, and simulations show a brutal galactic smash-up could have torn away its globulars, leaving behind only the most tightly bound survivors. Imagine a piñata, cracking open some candy scatters, but a few stubborn pieces cling inside. Here's where it gets stranger. The pinwheel's few remaining globulars aren't just sparse, they're oddly distributed. Instead of orbiting in a neat halo like other galaxies, they're clustered asymmetrically, as if huddling for safety on one side. This skewed arrangement fuels speculation that the galaxy might still be recovering from a near-fatal encounter, its stolen clusters now drifting in the wake of whatever wounded it. Yet the darkest twist, some globulars might not be missing at all, just invisible. A fraction could have plunged into the pinwheel's core over eons, consumed by its central black hole, if it exists, or dissolved into the stellar haze. Others might be camouflaged behind curtains of dust, their light dimmed to near nothingness. The pinwheel's globular cluster mystery forces us to confront a deeper question: how much of a galaxy's history can simply vanish? If these absent clusters hold the key to its past, their disappearance isn't just a puzzle, it's a cosmic crime scene, with clues scattered across 25 million light-years of silence. And until we find them, the pinwheel's origins remain half erased, like a story with its most crucial pages torn out. Hydrogen gas should be the great equalizer in galaxies, spread smoothly like butter across the cosmic bread of a spiral disk. But the Pinwheel Galaxy didn't get the memo. Its hydrogen distribution isn't just uneven, it's downright lopsided, with some regions so dense they could birth stars for eons, while others stretch thin like cosmic deserts. This isn't a minor imbalance, it's a fundamental fracture in how we expect galaxies to store their fuel, and the implications are staggering. Take the galaxy's northeastern quadrant, for instance. Radio telescopes reveal a sprawling hydrogen reservoir so thick it blots out other wavelengths, a murky ocean of gas where stars could form for billions of years untouched. Yet just across the spiral arm, the gas thins to a whisper, as if someone siphoned it away. This jagged asymmetry defies the pinwheel's otherwise elegant symmetry, like a painting where one corner is slathered in pigment and the rest barely sketched. What could cause such drastic unevenness? The prime suspect is the pinwheel's violent past. Galactic collisions don't just shuffle stars, they churn gas into unpredictable eddies. If a smaller galaxy once barreled through the pinwheel's disk, the gravitational turbulence might have herded hydrogen into dense pockets, leaving other regions starved. Picture a spoon dragged through syrup. Some clumps gather thickly while streaks of bare plate show through, but there's another subtler force at play: supernova feedback. In gas-rich galaxies, dying stars act like cosmic sculptors. Their explosive deaths blast away nearby hydrogen, carving bubbles in the interstellar medium. Normally, this process balances out, but in the pinwheel, something's broken the equilibrium. Perhaps supernovas in certain regions are clustered so tightly their combined shockwaves push gas farther than models predict, creating unnatural voids. Or maybe the galaxy's magnetic fields, stronger in some areas than others, are funneling gas like invisible railroads, guiding it toward specific zones. The real mystery isn't just where the hydrogen has gone, it's what this means for the pinwheel's future. Star formation thrives on dense gas, so these lopsided reserves could seed a stellar baby boom in one corner of the galaxy while condemning another to stagnation. Over time, this imbalance might warp the pinwheel's structure, twisting its arms asymmetrically as gravity tugs harder on the gas-heavy side. Yet the oddest detail: some of the densest hydrogen clouds don't align with visible star-forming regions. It's as if the galaxy is stockpiling fuel it doesn't yet know how to use, or waiting for a trigger we haven't witnessed. Whether by ancient violence, hidden forces, or sheer cosmic whim, the pinwheel's gas distribution is a puzzle with no easy solution. And until we crack it, we're left staring at a galaxy that plays by its own rules, one uneven breath of hydrogen at a time. Scattered across the Pinwheel Galaxy like cosmic puncture wounds, vast regions of eerie nothingness gape where hydrogen gas should be. Astronomers call them HI holes, not just empty patches, but voids so deep and abrupt they defy simple explanation. These aren't gentle dips in the gas map, they're sheer cliffs with edges so sharp they look carved by invisible blades, and their existence raises a chilling question: what force could possibly hollow out a galaxy with such surgical precision? Start with the usual suspects: supernova. When massive stars die in fiery explosions, their shockwaves can blast away surrounding gas, leaving behind expanding bubbles. The pinwheel's frenzied star-forming regions should be pockmarked with these supernova remnants, but there's a problem. The largest HI holes span hundreds of light years, far wider than any single stellar explosion could produce. Even multiple supernova working in concert would struggle to excavate voids this colossal. It's like trying to dig the Grand Canyon with firecrackers. The scale just doesn't add up. Then there's the stellar wind theory. Young, hot stars don't just shine, they scream into the void, ejecting supersonic streams of charged particles that push gas outward like cosmic plows. In clusters, these winds might combine to scour larger cavities. Yet when astronomers trace the pinwheel's stellar populations, many HI holes sit alarmingly far from any known clusters, adrift in gas-rich regions with no obvious power source. It's as if something reached in from the shadows, scooped out the hydrogen, and vanished without a trace. This brings us to the darker possibilities, literally. Could clumps of dark matter, drifting like invisible icebergs through the galaxy, have collided with these regions? Some models suggest dense knots of dark matter might gravitationally repel hydrogen gas, shoving it aside to create voids. Others propose even wilder scenarios: primordial black holes, left over from the Big Bang, passing through the pinwheel's disk and drinking the gas as they go. But the real enigma lies in the hole's shapes. Unlike the ragged bubbles left by supernova, some of these voids are nearly perfect spheres, their edges too smooth for known astrophysical processes. A few even appear stacked or aligned, as if part of some larger, unseen pattern. Are we witnessing the aftermath of a cataclysm we can't yet imagine, or the fingerprints of physics operating beyond our current theories? Every gap in the pinwheel's hydrogen map is a silent challenge, a reminder that even the building blocks of galaxies can vanish without explanation. And until we solve the riddle of these ghostly hollows, we're left staring into the abyss, wondering what else might be hiding in plain sight. The Pinwheel Galaxy doesn't just form stars, it builds them on a scale that dwarfs anything in our cosmic neighborhood. Nestled within its spiral arms are monstrous stellar cities known as superstar clusters, each packing hundreds of thousands of suns into spaces smaller than the distance between our sun and its nearest neighbor. These aren't your average star clusters, they're cosmic skyscrapers, so massive and dense they blur the line between modern clusters and ancient globulars. And their existence forces us to ask, what kind of extreme environment could possibly forge such stellar megalopolises? Picture the Orion Nebula, our local stellar nursery, then multiply its star density by 1,000 and compress it into a space 10 times smaller. That's the scale we're dealing with. Superstar clusters glow so brightly they outshine entire dwarf galaxies, their collective light visible across intergalactic distances. The Pinwheel's most famous example, NGC 5462, burns with the intensity of 10 million suns, its core so packed that stars there orbit just light days apart. If you stood on a planet in one of these clusters, your night sky would blaze with countless stars as bright as our full moon, an eternal, daylight-like glow from stellar neighbors practically close enough to touch. What makes these clusters so baffling isn't just their size. It's their scarcity in galaxies like our Milky Way. While the Pinwheel boasts dozens of superstar clusters, our home galaxy manages only a handful. The difference lies in their birth conditions. Superstar clusters require pristine clouds of gas hundreds of times more massive than typical nurseries, collapsing under near-perfect conditions. Most galaxies, including ours, lack the raw materials or the violent triggers needed to jumpstart such extreme star formation. But the Pinwheel, it's practically drowning in fuel, its spiral arms still rich with the primordial hydrogen that other galaxies burned through billions of years ago. Yet raw materials alone don't explain their survival. In most galaxies, clusters this young would be torn apart by gravitational tides or evaporated by supernova explosions before they could stabilize. The Pinwheel's secret might lie in its unusually calm galactic neighborhood, a cosmic backwater where these fragile giants can mature undisturbed. Or perhaps its clusters form differently, with tighter initial packing that helps them weather the storms of youth. Some even show signs of multiple generations of stars, suggesting they somehow retained enough gas to fuel successive waves of star birth, a feat thought impossible until we saw it here. The real game changer, these clusters might be modern globulars in the making. Ancient globular clusters orbiting our Milky Way were long thought to be relics of the early universe, their formation processes lost to time. But the Pinwheel superstar clusters are their spitting image, just billions of years younger. If they survive another 10 billion years, they could become near-perfect copies of the globulars we revere today. That means we might be witnessing, for the first time, how the universe's most enduring stellar structures are born. Every superstar cluster in the Pinwheel Galaxy is a time capsule, preserving the violent, gas-rich conditions of the early universe in a contemporary setting. They're not just cosmic oddities, they're living fossils, showing us how galaxies built their most spectacular structures when the cosmos was young. And as we study them, we're forced to wonder, is the Pinwheel showing us the past, or is it showing us what most galaxies could have been, if only they'd held onto their primordial fire a little longer? Among the Pinwheel Galaxy's countless stars, a peculiar group of celestial lanterns flicker with a rhythm that defies the cosmic rulebook. Cepheids variables, the universe's standard candles, are supposed to pulse with clockwork regularity, their brightness waxing and waning in predictable cycles that help astronomers measure vast distances across space. But in the Pinwheel, some of these stars are staging a rebellion. Their light curves stutter, jump, or even flatline unpredictably, like a faulty street lamp flickering in a cosmic wind. This isn't just a technical inconvenience, it's a crack in one of astronomy's most trusted tools, and the implications ripple far beyond this single galaxy. Take the case of a Cepheid catalogued as M101V1. For decades, it followed its expected rhythm, swelling and dimming every 37 days like a heartbeat. Then, without warning, its pulsations grew erratic. Brightness peaks arrived late or early, sometimes doubling in intensity, other times barely registering. It's as if the star's internal metronome suddenly broke. Traditional models blame such disruptions on mode switching, where a star's pulsations jump between different harmonic states. But the Pinwheel's erratic cepheids take this chaos further, displaying patterns so irregular they challenge our very understanding of stellar physics. One compelling explanation lurks in the shadows, unseen stellar companions. Many cepheids orbit in binary systems, their dance partners invisible to telescopes but palpable in their gravitational tug. If a companion star's orbit brings it close enough, its gravity could distort the cepheid's outer layers, interrupting the delicate balance between radiation pressure and gravity that drives the pulsations. Imagine blowing up a balloon while someone randomly squeezes it. The inflation becomes unpredictable. In extreme cases, these interactions might even strip material from the cepheid, altering its mass and disrupting its rhythm permanently. Yet binary mischief can't explain every anomaly. Some flickering cepheids show no trace of companions, their instability seeming to bubble up from within. Here, the culprit might be the star's own turbulent interiors. Cepheids pulse because their outer layers act like cosmic heat engines, trapping radiation until pressure builds and the star expands, only to cool and contract again. But in the Pinwheel's metal-poor environment where elements heavier than hydrogen and helium are scarce, this process might falter. With fewer atoms to absorb and re-emit radiation, the pulsation mechanism could grow unstable, like an engine misfiring when its fuel mix is wrong. The stakes of this mystery couldn't be higher. Cepheids are the yardsticks by which we measure the universe. When Edwin Hubble used them to prove the Andromeda Galaxy lay beyond the Milky Way, he relied on their steady rhythms. Now the Pinwheel's misbehaving variables threaten to warp that cosmic ruler. If their distances can't be trusted, how many other measurements from galaxy trajectories to the expansion rate of the universe might need recalibration? Perhaps the most tantalizing possibility is that we're witnessing stellar evolution in real time. Cepheids occupy a brief, volatile phase in a star's life, and the Pinwheel's intense star-forming environment might be pushing them into uncharted territory. Like canaries in a coal mine, these flickering giants could be signaling conditions we've never seen before, a hidden chapter in the life story of stars. Until we decode their erratic language, every pulse and pause remains a cosmic question mark. Amid the Pinwheel Galaxy's tapestry of starlight, there's a curious sight: tiny, glowing embers of green, no larger than a pixel in most telescopes, yet blazing with the fury of 1,000 suns. These aren't supernova or nebulae, but something far stranger. Compact knots of star formation so intense they've earned the nickname green pea analogues after their distant cosmic cousins. And their existence in the Pinwheel isn't just a quirk. It's a time machine offering a glimpse into the chaotic dawn of the universe. What makes these regions stand out isn't just their color, a peculiar greenish hue caused by overheated oxygen atoms, but their off-the-charts energy. Each pea crams hundreds of newborn stars into a space smaller than our solar system, their collective radiation ionizing surrounding gas until it fluoresces like a cosmic neon sign. To put that in perspective, if you plopped one of these peas into the Orion Nebula, it would outshine every star there combined. Yet despite their brilliance, they're almost ghostly in structure. No sprawling spiral arms or dusty lanes, just raw, unfiltered stellar genesis packed into a tiny, seething package. The real magic lies in their resemblance to green pea galaxies, a rare class of tiny, distant galaxies discovered in the mid-2000s. These far-off peas are thought to mimic conditions in the early universe, when galaxies were smaller, gas was purer, and stars formed in frantic bursts. But studying them is like trying to decipher a message written in faint, ancient ink. Their light takes billions of years to reach us, stretched and dimmed by cosmic expansion. The pinwheel's P's, by contrast, are right in our backyard, offering a crisp, close-up view of similar physics in action. So why does this galaxy, 25 million light-years away, harbor pockets that behave like relics from 13 billion years ago? The answer might lie in its primordial gas reserves. Unlike most mature galaxies where successive generations of stars have polluted interstellar gas with heavy elements, the pinwheel still holds vast clouds of near-pristine hydrogen fuel almost untouched since the universe's youth. When star formation ignites in these chemically simple regions, it mirrors the unbridled firestorms of the early cosmos, where gravity's grip went unchecked by the stabilizing influence of metals. Yet the pinwheel's P's aren't perfect replicas. Some show subtle differences, slightly higher metal content, or star clusters that are marginally more organized, hinting at how even these time capsules evolve. That's what makes them so valuable. They're not just snapshots, but living experiments in how the first galaxies grew up. Every flicker of their green glow carries data on how stars formed when the universe was raw and untamed, and how those processes shaped everything that followed. Perhaps most intriguing is what they suggest about the pinwheel's role in cosmic history. This galaxy isn't just a collection of oddities. It's a bridge between epochs, preserving ancient modes of star formation long after most galaxies moved on. In its greenest corners, the universe's past still burns bright, waiting for us to decode its secrets. And with each observation, we're not just studying a single galaxy's quirks, we're piecing together the origin story of everything. The Pinwheel Galaxy is supposed to be the poster child for pristine, unbarred spirals, its arms unfurling smoothly from the core like water spiraling down a drain. But a growing chorus of astronomers suspects this cosmic pinwheel might be hiding a skeleton in its closet, an invisible bar structure lurking just beneath the surface of its graceful swirl. If true, it would rewrite not just the pinwheel's identity, but our entire playbook for how galaxies evolve. Bars are cosmic traffic jams, dense lanes of stars stretching across galactic centers, funneling gas inward like celestial conveyor belts. They're thought to be engines of change, reshaping galaxies by fueling star formation in their cores and eventually dissolving into the spiral arms we see today. Most barred galaxies advertise their structure with obvious straight lines of starlight, but the pinwheel's supposed lack of one has long been a point of pride in astronomy textbooks. Yet the evidence for a hidden bar is mounting. Infrared observations pierce through the galaxy's dust, revealing subtle asymmetries in the motion of stars near its core, swirling patterns that only make sense if an elongated mass is tugging them off course. Computer simulations show similar distortions when barred galaxies are viewed nearly face-on, their bars camouflaged by perspective. And then there's the gas, streams of hydrogen converging toward the center at odd angles, as if guided by an unseen hand. This isn't just academic quibbling. Bars are galactic pacemakers, regulating how quickly a galaxy consumes its gas reserves. If the pinwheel secretly harbors one, it could explain why it's still birthing stars at a feverish clip while other galaxies its age have settled into quiet middle age. A bar would have efficiently funneled gas inward over eons, stockpiling fuel for future stellar generations while less efficient galaxies burned out. The implications get wilder. Some models suggest bars self-destruct their own gravitational turbulence, eventually causing them to buckle and dissolve. If the pinwheel's bar is in its death throes, barely detectable yet still influencing its surroundings, we might be witnessing the final act of a transformation billions of years in the making. It would mean the pinwheel isn't the untouched archetype we thought, but a reformed barred galaxy entering its next chapter, but the boldest claim that we're seeing a bar in its infancy. Perhaps the pinwheel is only now growing one, triggered by a past galactic encounter or some internal instability. This would flip the script entirely, suggesting even seemingly pure spirals can develop bars late in life, a cosmic midlife crisis played out in stars and gas. For now, the debate rages on. Every new observation adds another piece to the puzzle, each one hinting that the pinwheel story is far more complex than its flawless spiral suggests. Whether relic or newborn, this phantom bar challenges us to rethink not just one galaxy's history, but the very rhythm of galactic evolution itself. And in that invisible structure, we might finally find the key to why the pinwheel dances to its own tune. The Pinwheel Galaxy has always presented itself as a perfect cosmic spiral, its stars and gas swirling in graceful harmony until you look closer. Beneath its photogenic surface, something's off-kilter. While the galaxy's stellar disk spins with textbook elegance, its vast reservoir of hydrogen gas is tilted, warped, almost drunkenly misaligned, like a record skipping on a turntable. This isn't just a minor wobble, it's a fundamental disconnect between two components that should move as one, and it hints at a history of cosmic violence we're only beginning to unravel. Gas disks don't just tilt on their own. Normally, the relentless pull of gravity aligns them with their galaxy's stellar disk over time, smoothing out any irregularities. So when astronomers mapped the pinwheel's hydrogen using radio telescopes, they expected to see a neat, flat plane mirroring the starlight. Instead, they found a gas disk leaning at a 15-degree angle, its outer edges twisting like a vinyl record left too close to a heat lamp. The mismatch is so stark it rules out random chance. Something forced this galaxy off balance. The prime suspect, a galactic merger. When two galaxies collide, their gas clouds don't just blend seamlessly, they slam together at odd angles, creating chaos that can take billions of years to settle. Imagine pouring cream into coffee while spinning the cup. The liquids mix unevenly, forming swirling, unstable layers. If a smaller galaxy grazed the pinwheel eons ago, its gas could have been dragged into this tilted configuration, leaving the stellar disk relatively unscathed. Supporting this, computer simulations show that even minor mergers, once too gentle to shred the pinwheel's iconic spiral, could warp its gas disk profoundly. But there's a twist. The gas tilt isn't uniform. Some regions bend more sharply than others, as if the disk is caught mid-wobble, still settling from the disturbance. This suggests the event might not be ancient history, it could be ongoing. The pinwheel might still be siphoning gas from a cosmic neighbor or accreting intergalactic material from the filamentary cosmic web that threads the universe. Like a tree tilting as its roots drink from an uneven water table, the galaxy's gas disk could be responding to fresh inflows from unpredictable directions. What's at stake isn't just a pretty spiral. A misaligned gas disk is a ticking time bomb for galactic stability. Gas fuels star formation, and when it's unevenly distributed, star birth can become lopsided, distorting the galaxy's shape over time. The pinwheel's graceful arms might eventually warp into something less photogenic, a lopsided mess of stellar clumps and twisted lanes. Worse, the torque from the tilted disk could funnel gas toward the core unpredictably, either starving future star formation or triggering violent bursts of activity near the center. Yet the pinwheel's resilience complicates the story. Despite the tilt, it's still one of the most symmetric spirals we know. This raises a provocative question. Are we witnessing a galaxy in the act of self-correction? Some models suggest magnetic fields woven through the gas like invisible wires might be slowly realigning the disk, fighting against the tilt's chaos. Or perhaps dark matter, distributed in some unseen pattern, is acting as a counterbalance, steadying the galaxy like a gyroscope in the void. Every observation deepens the mystery. The tilted gas disk isn't just an oddity, it's a ledger of the pinwheel's past collisions, a tracer of the invisible forces shaping its future, and a challenge to our assumptions about how galaxies maintain their equilibrium. And as we study it, we're left wondering, is this cosmic wobble a relic of turbulence long past or the first tremor of a transformation yet to come? Tucked away in the Pinwheel Galaxy's outer reaches, an enigmatic loop of radio waves drifts through the void, a ghostly structure with no visible counterpart. Unlike the vibrant nebulae and star clusters that decorate most telescopic images, this feature reveals itself only in the cold, silent language of radio frequencies, glowing faintly against the cosmic backdrop. It's not a supernova remnant, not a jet from a black hole, not anything we've seen before, and its very existence forces us to confront a chilling question. What kind of cosmic event leaves behind only a whisper in the radio spectrum, fading but never quite vanishing? This loop isn't just unusual, it's improbable. Radio structures in galaxies typically trace violent processes, the searing aftermath of exploded stars, the magnetized footprints of pulsars, or the focused beams of active black holes. Yet this loop lacks the hallmarks of all three. There's no X-ray glow hinting at a central energy source, no shell of expanding debris, no twisted magnetic fields that usually accompany such remnants. Instead, it hangs in space like a cosmic smoke ring, a relic of something far stranger. One theory points to an ancient cataclysm, a tidal disruption event where a star strayed too close to a black hole and was torn apart. The resulting shockwave could have blasted material outward in a symmetrical loop, its visible light long faded but its radio echo lingering. Picture a stone dropped in a pond. The ripples spread, then vanish, but if you could listen to the water's subtle vibrations, you might still trace their ghostly imprint. Alternatively, this could be the fossilized jet of a once active supermassive black hole. Its beam flicked off eons ago like a forgotten lighthouse, leaving only a fading ripple in the interstellar medium. Yet even these explanations strain under scrutiny. The loop's symmetry is too perfect, its edges too crisp for something born from chaos, and its location far from the galactic core rules out most black hole-related scenarios. Which raises the wilder possibility: could this be the scar of an intergalactic collision? If a dense knot of dark matter or a rogue black hole punched through the pinwheel's disk, the gravitational shockwave might have stirred the galaxy's magnetic fields into this eerie, coherent shape. The loop's persistence is equally baffling. Without an ongoing energy source, such structures should dissipate within millions of years. That this one endures suggests either a recent event, unlikely given the lack of accompanying fireworks, or some hidden mechanism replenishing its energy, like cosmic rays threading through the loop's filaments like invisible live wires. What makes this mystery so tantalizing is its silence. Most cosmic phenomena scream their presence across multiple wavelengths, but this loop speaks only in radiostatic, a cipher waiting to be decoded. And until we do, it remains a haunting reminder. Sometimes the universe's quietest whispers carry its most profound secrets. The Pinwheel Galaxy isn't just forming stars, it's forging monsters. Scattered across its spiral arms like cosmic flamethrowers, an extraordinary number of Wolf-Rayet stars burn with a ferocity that defies the odds. These aren't your average celestial bodies. They're the rarest, most extreme stars in the universe, massive, unstable, and destined to die in spectacular supernova. And the Pinwheel doesn't just have a handful of them. It's practically drowning in these stellar anomalies, boasting more Wolf-Rayet stars than nearly any galaxy of its size. What makes these stars so special? Imagine a sun 20 times heavier than our own, its outer layers stripped away by hurricane-force stellar winds, exposing a core hot enough to fuse elements like titanium and chromium in its furnace. Wolf-Rayet stars shine with an eerie blue-white glare, their surfaces racked by turbulence so violent they shed entire Earth masses of material every year. They're stars living on borrowed time, cosmic fireworks poised to detonate. The Pinwheel's abundance of these rare giants points to a perfect storm of conditions. First, its relentless star-forming frenzy provides the raw material, vast clouds of gas collapsing into exceptionally massive stars. Second, the galaxy's low metallicity. Its scarcity of heavy elements allows these stars to retain more mass as they form, avoiding the destructive feedback that usually limits their size in richer environments. It's like baking a cake with fewer ingredients and somehow ending up with a towering, unstable masterpiece. But here's the twist: Wolf-Rayet stars are more than just curiosities, they're galactic game changers. Their blistering winds seed surrounding space with carbon, nitrogen, and oxygen, the building blocks of future planets and life. And when they inevitably explode, their supernova will flood the pinwheel with even heavier elements, from gold to uranium. This galaxy isn't just hoarding these stars, it's stockpiling the ingredients for its own cosmic renaissance. Yet the sheer number of Wolf-Rayet stars raises a troubling question. What happens when they all go off? Unlike typical supernova, which pepper a galaxy sporadically, the pinwheel's Wolf-Rayet population could trigger a chain reaction of detonations, a starburst of death that might reshape entire spiral arms. Some models suggest clustered supernova could blow vast cavities in the interstellar medium, carving bubbles so large they'd alter the galaxy's structure for eons. Others speculate the combined shockwaves might even compress nearby gas, triggering yet more star formation in a self-perpetuating cycle. The pinwheel's Wolf-Rayet surplus isn't just a quirk, it's a ticking time bomb of cosmic evolution. And as we watch these stars burn through their furious lives, we're witnessing a preview of the galaxy's explosive future, one where death begets creation on a scale that dwarfs our wildest imaginations. Deep in the Pinwheel Galaxy's spiral arms, clusters of stars huddle together with a gravitational grip that shouldn't be possible. These aren't your average star clusters, they're cosmic anomalies, their collective mass far outweighing the visible stars they contain. Astronomers call them dark star clusters, and their existence hinges on one radical idea. What if these glittering knots of starlight are secretly dominated by dark matter, their true heft hidden in the void between the stars? The pinwheel's peculiar clusters might just hold the key to proving this controversial theory, or appending it entirely. Take one of the galaxy's largest clusters and you see 5466. By all appearances, it's a typical globular, a dense ball of ancient stars orbiting the galactic core. But when researchers measured its velocity dispersion, how fast its stars zip around, they got a shock. The stars move too quickly, as if shackled by an unseen gravitational anchor. Visible matter accounts for barely half the mass needed to explain their motion. The rest, either we've misunderstood stellar physics or something invisible is lurking there, pulling the strings. This isn't just a pinwheel oddity. A handful of similar clusters pepper other galaxies, always with the same mismatch: too much gravity, too few stars. The leading explanation: dark matter, that enigmatic substance outweighing visible matter 5-to-1 in the cosmos. Most globular clusters are thought to be clean of dark matter, forming from gas pockets that collapsed early in the universe's history. But if some were born within primordial dark matter clumps or later captured by them, they might retain hidden halos like fireflies trapped in lumps of invisible amber. Critics counter with alternative explanations. Perhaps these clusters are simply richer in stellar remnants, black holes, and neutron stars than we can detect. A few dozen compact objects could masquerade as dark matter's gravitational signature. Others suggest tidal stripping. If a cluster passed too close to the galactic center, gravity might have ripped away its outer stars, leaving behind a deceptively dense core that looks heavier than it is. The pinwheel's clusters add a fascinating wrinkle. Unlike Milky Way globulars, which orbit in predictable paths, some of the pinwheel's suspect clusters drift oddly, their trajectories suggesting interactions with unseen mass. Even stranger, a few appear to be young by cosmic standards, unlike the ancient globulars where dark matter should have dissipated long ago. If confirmed, this could mean dark matter isn't just clinging to these clusters. It might be actively shaping their evolution, a shadowy puppeteer guiding stellar destinies. The implications are staggering. If dark star clusters exist, they're cosmic Rosetta Stones, offering a chance to study dark matter's behavior on scales small enough to test in simulations. Do their dark halos mimic the smooth distributions predicted by theory, or do they clump unpredictably? And why do only some clusters seem affected? The pinwheel's peculiar collections could help crack these questions, or force us to rewrite the rules once again. For now, the mystery lingers. Every anomalous cluster in the Pinwheel Galaxy is a gravitational riddle, a celestial tug of war between what we see and what we know must be there. Whether future observations vindicate the dark matter hypothesis or send us back to the drawing board, one thing's certain: these clusters are hiding secrets that could reshape our understanding of the universe's hidden architecture. And the pinwheel, ever the cosmic rebel, seems determined to keep us guessing. The Pinwheel Galaxy's supernova remnants tell a story that doesn't quite add up. Scattered across its spiral arms, these expanding shells of debris appear too old for a galaxy still bursting with youthful vigor. Most galaxies match their supernova remnants to their star-forming history like chapters in a book. The pinwheel, however, seems to have pages torn from an entirely different volume. Some of these remnants stretch hundreds of light years, their shockwaves faded to whispers, suggesting explosions that occurred billions of years ago. Yet the galaxy's busiest star-forming regions where massive stars live fast and die young hint that such ancient supernovas shouldn't exist here at all. It's like finding fossils in a nursery, remnants of a bygone era stubbornly lingering where they don't belong. So how does a galaxy still churning out new stars at a breakneck pace end up with supernova remnants older than its youngest neighborhoods? One possibility is delayed triggers stellar time bombs that took eons to detonate. Imagine a binary star system where one star collapses into a white dwarf, slowly siphoning material from its companion until it crosses a critical mass and explodes as a Type 1, a supernova. These delayed explosions could occur long after the stars originally formed, creating remnants that appear out of sync with their surroundings. Alternatively, some massive stars might defy expectations by burning their fuel far slower than models predict, extending their lifespans and postponing their fiery deaths by millions of years. The pinwheel's unique chemistry, lower in heavy elements than our Milky Way, could be the wild card, altering how stars age in ways we're only beginning to understand. Then there's the measurement problem. Estimating a supernova remnant's age isn't as simple as reading a cosmic clock. Astronomers typically calculate ages by measuring how fast the debris expands and tracing it backward to the moment of explosion. But what if the remnants didn't expand uniformly? Dense pockets of interstellar gas could break some regions like celestial speed bumps, while others race ahead, creating illusions of greater age. The pinwheel's lopsided hydrogen distribution might be skewing the numbers, camouflaging younger remnants as ancient relics. But the most provocative explanation challenges our assumptions about the pinwheel's history itself. What if these old remnants are actually refugees, ghosts of supernova that erupted in a smaller galaxy long before it merged with the pinwheel? Galactic collisions don't just shuffle stars. They can strew stellar corpses across new environments, like scattering ashes in a foreign wind. If the pinwheel cannibalized a dwarf galaxy billions of years ago, it could have inherited pre-existing remnants that now drift incongruously among its younger structures. The implications ripple far beyond one galaxy's oddities. If supernova can delay their explosions or masquerade as older than they are, our cosmic timelines for star formation and death might need recalibrating. The pinwheel's paradoxical remnants aren't just celestial quirks, they're stopwatches that might be ticking differently than we thought. And until we solve their riddle, we can't fully trust the age of anything in the cosmos. The Pinwheel Galaxy doesn't dance alone. It's surrounded by a troop of dwarf galaxies, each moving in ways that defy the usual cosmic choreography. These tiny companions don't orbit in neat, predictable circles. Instead, they pirouette erratically, some hurtling toward the pinwheel at breakneck speeds, others drifting away as if repelled by an unseen force. Astronomers can't agree on whether these dwarfs are true satellites. bound by gravity to the pinwheel, or just passing interlopers caught in a fleeting cosmic tango. But one thing's certain, their chaotic motions are leaving fingerprints all over the pinwheel's structure, reshaping our understanding of how galaxies grow and interact. Take one of the most puzzling examples, a dwarf galaxy catalogued as M101DF3. Unlike most satellites which orbit in roughly the same plane as their host galaxy, this rebel loops around the pinwheel's poles, tracing a path more akin to a comet than a loyal moon. Its trajectory suggests it might not belong here at all. It could be a visitor from intergalactic space, snared by the pinwheel's gravity during a chance encounter. Yet its stars bear a striking chemical resemblance to the pinwheel's outer halo, hinting at a shared history. Is it a long-lost sibling or just a stranger wearing familiar clothes? Then there's the speed problem. Some of these dwarfs move too fast to be bound by the pinwheel's gravity alone. Traditional models predict that satellite galaxies should orbit at velocities balanced by their hosts' pull like stones swung on strings. But several of the pinwheel's companions exceed these predicted speeds, as if their strings were cut mid-swing. One explanation: dark matter. If the pinwheel's dark halo is lumpier than we've assumed, its uneven gravity could be slingshotting dwarfs to unexpected velocities. Alternatively, these speedsters might be fresh captures, still bleeding off energy from their initial plunge into the pinwheel's grasp. The most tantalizing clue lies in the pinwheel's warped gas disk and fractured spiral arms. Computer simulations show that dwarf galaxies don't just orbit passively, they stir their hosts. As they pass through or near a larger galaxy, their gravity can tug on gas clouds and stars, bending disks and triggering waves of star formation. The pinwheel's lopsided hydrogen distribution and those phantom spiral arms could both be scars from ancient dwarf encounters, cosmic bruises left by these tiny but influential partners. Yet the dwarfs themselves tell a darker story. Some appear stretched, their stars pulled into long, faint streams, the telltale sign of tidal disruption. The pinwheel's gravity is slowly shredding them, digesting their stars into its own halo. This cannibalistic process, known as hierarchical merging, is how galaxies grow over time. But here's the twist: the pinwheel's dwarfs are vanishing faster than expected, as if something, perhaps an unseen dark matter subhalo, is accelerating their destruction. The ultimate question isn't just about these dwarfs' origins, but their fate. Are they doomed to be absorbed, or will some escape entirely, fleeing into the void like cosmic runaways? Their chaotic dance doesn't just shape the pinwheel, it challenges our assumptions about how galaxies evolve. Every erratic orbit, every stretched stellar stream, is a reminder that even the smallest players can alter the grandest stages of the universe. The Pinwheel Galaxy has a thermal secret. It's glowing hotter than it should. When astronomers measured its infrared output, the numbers came back off the charts, revealing an unexpected excess of heat radiating from its spiral arms. This isn't just a minor discrepancy, it's a full-blown cosmic anomaly, with the galaxy pumping out up to 30% more infrared light than its visible starlight can explain. So where's all this extra warmth coming from? The answer might rewrite how we understand the hidden mechanics of spiral galaxies. Start with the obvious suspect: dust. Galaxies are littered with microscopic grains of carbon and silicon, the cosmic equivalent of soot and sand. When starlight hits these particles, they absorb the energy and re-emit it as infrared radiation. The pinwheel's vigorous star formation should produce plenty of dust. But here's the catch: the dust we can see doesn't account for the sheer volume of infrared glow. That means either our telescopes are missing vast reservoirs of hidden dust, or something far stranger is at work. One theory points to ultra-dense dust clouds clustered near the galaxy's core. These murky fortresses could be so thick they're completely opaque to visible light, hiding their true scale while still radiating heat. Imagine a fog so dense you can't see through it, yet it hums with warmth you can feel from a distance. These shrouded dust banks might be the pinwheel's best-kept secret, absorbing starlight like cosmic sponges and re-radiating it in wavelengths we can't directly see. Then there's the wild card, an active galactic nucleus or AN. Most galaxies host a supermassive black hole at their center, and when these monsters feed, they heat surrounding dust to extreme temperatures, creating a secondary infrared beacon. The pinwheel's missing central black hole makes this explanation tricky but not impossible. A cloaked AGN buried under layers of gas and dust could still be firing up the galaxy's thermal signature without revealing itself in other wavelengths. It's like hearing an engine roar through a closed garage door. You can't see the source, but you know it's there. But the most tantalizing possibility involves the pinwheel's peculiar stellar demographics. This galaxy is overflowing with massive, short-lived stars that burn fiercely and die young. These stellar powerhouses blast out ultraviolet radiation, which gets downshifted to infrared by surrounding dust. If the pinwheel's star-forming regions are skewed toward producing more of these luminous giants than average, their collective UV output could be supercharging the galaxy's thermal afterglow beyond anything we've modeled. The implications ripple far beyond one galaxy's odd glow. If hidden dust or rogue stellar populations are responsible, it means our census of cosmic materials is incomplete. Galaxies might be hoarding more matter than we can detect. If an AGN is the culprit, it challenges our assumptions about how central black holes influence their hosts even when invisible. Every photon of that excess infrared light is a clue, a whisper from the pinwheel that says, "Look closer." Because in the end, this isn't just about heat. It's about all the things a galaxy can hide in plain sight. The Pinwheel Galaxy's magnetic fields are staging their own quiet rebellion, stretching across its spiral arms in patterns that shouldn't exist, as if drawn by an invisible hand. Normally, a galaxy's magnetic fields follow its structure like threads woven through fabric, tracing the graceful curves of spiral arms where star formation stirs interstellar chaos. But here, vast regions of the pinwheel's magnetism stand defiantly perpendicular to its swirls, forming eerie grid lines across the cosmic canvas. These aren't just minor kinks in the galactic tapestry. They're full-scale anomalies, their rigid alignment clashing with everything we know about how magnetic fields behave in spirals. So how does a galaxy break the rules of magnetism? The prime suspect is turbulence violence written into the pinwheel's history. When galaxies collide or merge, their gravitational upheaval doesn't just shuffle stars, it twists and amplifies magnetic fields like taffy, stretching them into unnatural configurations. Imagine dragging a comb through a vat of molten iron, then freezing the ripples mid-motion. A past encounter with another galaxy could have wrenched the pinwheel's fields into this strange alignment, leaving behind fossilized magnetism long after the collision's visible scars faded. But there's a catch: magnetic fields shouldn't stay twisted forever. Over time, the motions of gas and stars should relax them back into harmony with the spiral arms. The fact that these phantom fields persist suggests something is actively maintaining them. Perhaps hidden flows of gas or dark matter, circulating like subterranean currents beneath the visible disk. Alternatively, the pinwheel's frenetic star formation might be pumping energy into the system, like a cosmic mixer churning the magnetic batter into stubborn new shapes. The most tantalizing clue lies in the field's locations. They're strongest in regions between the spiral arms where gas is thinner and star formation is sparse. This rules out the usual suspects: no bustling stellar nurseries or supernova shockwaves to explain the distortion. Instead, astronomers are left with two radical possibilities. Either the pinwheel's magnetic fields are being shaped by forces we can't yet detect, or our understanding of galactic magnetism is fundamentally incomplete. Some theorists point to cosmic rays, high-energy particles racing through the galaxy as potential sculptors. These subatomic bullets could be dragging magnetic field lines with them as they spiral through space, weaving the observed grid lines like invisible looms. Others suggest the fields might be relics from the pinwheel's infancy, frozen into place during its formation and somehow resisting the galaxy's later evolution. It's the cosmic equivalent of finding a childhood fingerprint preserved in cement, untouched by decades of weather. What makes these phantom fields more than a curiosity is their power to shape the galaxy's future. Magnetic fields guide the collapse of gas clouds, channel star-forming material, and even influence the trajectories of cosmic rays. If the pinwheel's fields are truly misaligned on such vast scales, they could be secretly orchestrating everything from stellar birth to the distribution of interstellar dust, rewriting the galaxy's destiny behind the scenes. And until we decode their origin, we're left staring at a cosmic puppet show, wondering who or what is pulling the strings. The Pinwheel Galaxy should be littered with planetary nebulae, those ethereal, glowing shells of gas exhaled by dying stars, yet they're vanishingly rare. For every 100 we'd expect to find based on the galaxy's stellar population, barely a handful appear in our telescopes. It's as if the pinwheel has a cosmic aversion to these beautiful stellar farewells, leaving astronomers to wonder, where did all the planetary nebulae go? These celestial wraiths aren't just pretty to look at, they're crucial pieces of a galaxy's life cycle. When a star like our Sun nears death, it swells into a red giant before shedding its outer layers in a gentle stellar wind, leaving behind a white dwarf at the center of a glowing gas cloud. The process should be universal, a standard finale for mid-sized stars across the cosmos. Yet in the pinwheel, something's interrupting this final act. Either the stars here are dying differently, or we're missing clues hidden in plain sight. One explanation cuts to the heart of the galaxy's star-forming frenzy. The pinwheel's low metallicity, its scarcity of heavy elements, might be altering how its stars age. In metal-poor environments, stellar winds can blow weaker or stronger than usual, either stripping stars too efficiently to form classic planetary nebulae or dumping material too diffusely to glow detectably. Imagine a candle snuffed out by a gust versus one that burns so slowly it never flares bright enough to see. The pinwheel's unique chemistry could be quietly rewriting the rules of stellar death. Then there's the observational hurdle. These nebulae fade fast, lasting only tens of thousands of years. A blink in cosmic time, they're easy to miss if surveys aren't perfectly timed. The pinwheel's distance adds another layer of difficulty. What would be a vivid, sprawling nebula in our galactic neighborhood might appear as a single dim pixel here. Compounding the challenge, the galaxy's thick dust lanes could be absorbing the nebulae's characteristic blue-green light, masking them behind curtains of cosmic soot. But the most tantalizing possibility, the pinwheel stars aren't playing by the standard in-game rules. Some might collapse directly into white dwarfs without the dramatic gas expulsion, like a firework that never ignites. Others could be merging with binary partners before they have a chance to puff away their outer layers, their deaths erased by gravitational theft. In regions teeming with stars, close encounters might even rip nascent nebulae apart before they fully form, scattering their gas into the interstellar void. This isn't just about missing objects, it's about rewriting stellar obituaries. If planetary nebulae are scarcer here than theory predicts, our models of how galaxies recycle material might need an overhaul. These glowing shells are factories for cosmic dust and complex molecules, the very ingredients for new stars and planets. A shortage could ripple across the pinwheel's evolution, leaving future stellar generations starved of essential materials. Or perhaps the galaxy has found another way to redistribute these elements, a process we've yet to unravel. Every absent nebula is a silent challenge, a reminder that even the most well-understood stellar processes can hide surprises. And in those gaps, the pinwheel whispers a question. Are we seeing a cosmic exception, or have we misunderstood the rule all along? Fast radio bursts those enigmatic cosmic signals that flash brighter than 1 billion suns for mere milliseconds have puzzled astronomers since their discovery. Most come from distant galaxies billions of light years away, But what if the Pinwheel Galaxy, right in our cosmic backyard, holds clues to their origin? Nestled among its chaotic star-forming regions and spinning magnetas, conditions might just be extreme enough to brew these mysterious eruptions. Start with the magnetas, neutron stars so magnetized they warp the very fabric of space around them. The pinwheel's abundance of these objects, left behind by supernova from its relentless stellar births, could be ticking time bombs. When a magneta's crust fractures under unimaginable magnetic stress, it might unleash a burst of energy so intense it ripples across the universe as a fast radio burst. Picture a cosmic earthquake where the aftershock isn't seismic waves but a scream of radio light. One of the pinwheel's magnetas, known as J0993, already exhibits erratic X-ray flares. Could its next tantrum be a radio burst visible across intergalactic space? Yet magnetas aren't the only suspects. The pinwheel star-forming cauldrons, like the supercluster NGC 5462, churn out massive stars that live fast and die violent deaths. Collisions between neutron stars or black holes in these crowded nurseries could generate shockwaves potent enough to emit fast radio bursts as parting gifts. Imagine two stellar corpses spiraling together in a gravitational death spiral, their final embrace unleashing a pulse of energy so focused it briefly outshines entire galaxies. Here's where it gets stranger: the pinwheel's low metal content. Unlike metal-rich galaxies where dense atmospheres might smother such signals, the pinwheel's relatively pristine gas could allow bursts to travel farther and clearer, like a shout in an empty canyon versus a crowded room. This might explain why we've yet to detect one from here. Our tools are tuned for distant, ancient bursts, not nearby whispers filtered through a cleaner cosmic medium. The tantalizing possibility: the pinwheel could be a Rosetta Stone for fast radio bursts. If one erupted here, we'd have a front row seat to study its environment in unparalleled detail, potentially cracking the code of these cosmic enigmas. Until then, every magneta flare, every neutron star collision in this galaxy carries the whisper of a question. Is the pinwheel hiding the key to one of the universe's loudest mysteries? At first glance, the Pinwheel Galaxy's core seems like textbook perfection, a dense, glowing hub where stars crowd together in a predictable ballet. But peer closer and something doesn't add up. Lurking just off-center, a faint smudge of light stubbornly persists in telescopic images, sparking whispers of a double nucleus, a second gravitational heart beating within the galaxy. This isn't just a blur or a trick of the light. It's a full-blown cosmic anomaly that could rewrite our understanding of how galaxies evolve, the leading theory. A captured dwarf galaxy. Imagine a smaller galaxy drawn inexorably into the pinwheel's grasp over billions of years. Instead of being torn apart entirely, its core, packed with ancient stars and perhaps even a small black hole, could have survived the merger, now orbiting just far enough from the primary nucleus to remain distinct. Supporting this, spectroscopic analysis reveals the secondary knot shares chemical fingerprints with known dwarf galaxies, older, metal-poor stars that stand in stark contrast to the pinwheel's younger central population. It's like finding a fossil embedded in modern bedrock, a relic of a long-ago collision. But skeptics aren't convinced. The alternative: a super-star cluster gone rogue. The pinwheel's spiral arms are littered with these dense stellar metropolises, and under the right conditions one could migrate inward, masquerading as a second nucleus. Proponents of this idea point to the object's compact size and blazing luminosity, both hallmarks of an overachieving cluster, yet even this explanation strains under scrutiny. No known star cluster, no matter how massive, should be able to hold itself together so close to the gravitational turmoil of a galactic core unless it's anchored by something extraordinary, like an intermediate mass black hole we've yet to detect. The plot thickens when we examine dynamics. If this were truly a captured dwarf, its orbit around the primary nucleus should leave gravitational fingerprint, subtle warps in the pinwheel's gas disk, or tidal streams of stars trailing behind. So far, the evidence is murky. Some observations hint at faint stellar tendrils arcing toward the outer galaxy, while others show nothing at all. Meanwhile, the secondary nucleus's motion defies easy categorization, neither cleanly orbiting nor fully merging. It's as if the galaxy itself can't decide whether this interloper belongs. Perhaps the most tantalizing clue comes from the pinwheel's missing supermassive black hole. If the primary nucleus is oddly quiet for a galaxy of this size, could the secondary hold the key? A black hole from a devoured dwarf, now lurking just off-center, might explain both the double nucleus illusion and the eerie silence at the galaxy's core. Alternatively, the two could be locked in a slow-motion dance, their gravitational tug of war stirring the pinwheel's gas into frenzied star formation while hiding their true nature. What makes this mystery so compelling is its stakes. If the pinwheel's double nucleus is real, it's a smoking gun for hierarchical galaxy formation, proof that galaxies grow by cannibalizing their neighbors. But if it's a supercluster or some unknown phenomenon, it forces us to reconsider how stars organize themselves in the universe's most extreme environments. Every photon from that faint smudge carries a question. Are we seeing a galactic crime scene, a cosmic mirage, or something entirely new? Until we crack this case, the pinwheel's secret second heart will keep pulsing just out of reach. The Pinwheel Galaxy isn't just spinning stars and gas. It's running a cosmic car wash, with vast geysers of gas shooting out from its disk only to rain back down in a celestial cycle astronomers call the galactic fountain. Picture this: supernova. The titanic explosions of dying stars act like pressurized nozzles, blasting heated gas thousands of light years above the galaxy's plane. But gravity always wins, pulling this material back down in shimmering arcs that cool and condense into fresh fuel for new stars. This isn't just a pretty cosmic spectacle. It's a self-regulating engine that determines how fast the pinwheel grows, how long its star-forming frenzy lasts, and even how its spiral arms maintain their shape against the chaos. The mechanics are both brutal and beautiful. When a massive star explodes as a supernova, the shockwave evacuates a cavity in the interstellar medium, hurling surrounding gas outward at speeds topping thousands of kilometers per second. Some of this material escapes entirely, lost to the intergalactic void, but much of it, especially the heavier elements forged in the star's core, is merely lofted high above the disk, where it forms a halo of hot, ionized plasma. Over millions of years, this gas cools, clumps, and cascades back down, often far from its origin point. It's like tossing a handful of confetti into a fan. The pieces spiral outward before drifting back to settle in unpredictable patterns. Here's where the pinwheel's fountain gets peculiar. Most galaxies' fountains are relatively balanced: gas expelled roughly equals gas returning. But the pinwheel's outflows appear lopsided, with some regions hemorrhaging material faster than it can rain back down. Infrared and radio telescopes reveal chimneys of gas towering over the galaxy's busiest star-forming zones, while other areas show barely a trickle. This imbalance suggests the pinwheel supernova aren't just randomly detonating fireworks. They're synchronized in clusters, their combined energy punching holes in the galactic disk like a sieve. The consequences ripple across the galaxy. Without this feedback cycle, the pinwheel would either exhaust its gas reserves too quickly, burning out in a blaze of short-lived stars, or stagnate, its gas locked in inert clouds. Instead, the fountain acts like a thermostat, with supernova both expelling gas to slow star formation and later recycling it to sustain future generations. Imagine a gardener who prunes a tree aggressively one season, only to use the clippings as compost for the next. Yet the pinwheel's version of this process holds a mystery. Some falling gas clouds are richer in metals elements heavier than hydrogen and helium than the regions where they land. This implies the fountain isn't just recycling. It's redistributing the galaxy's building blocks in ways that could rewrite the chemistry of future stars. A newborn star forming from this enriched rain might inherit a completely different elemental blueprint than its neighbors, like a child raised on imported spices instead of local ingredients. The ultimate question is whether this frenetic churn is unique to the pinwheel or a hidden universal rhythm. Most galaxies show some evidence of fountaining, but none as dramatic or as lopsided. Is this imbalance a temporary glitch, a sign of the pinwheel's recent star-forming spree, or a permanent feature of its chaotic heartbeat? Every droplet of gas flowing back into this galaxy carries clues, not just about its own future, but about how all galaxies sculpt themselves through cycles of destruction and rebirth. Buried within the Pinwheel Galaxy's swirling arms, patches of dust glow with a chill that defies logic, regions so cold they barely register above the cosmic background temperature. At just 15 to 20 degrees above absolute zero, these frosty particles shouldn't exist in such proximity to the galaxy's blazing star clusters and supernova remnants. Cold dust isn't unheard of in space, but it typically lingers in the frigid voids between galaxies, not nestled inside a vibrant spiral like the pinwheel. The real puzzle: these icy pockets show no trace of nearby heat sources that could explain why they haven't warmed up, as if the galaxy itself has hidden refrigerators scattered through its starry tapestry. One possible culprit hides in the shadows: dark matter. Some theoretical models suggest that when dark matter particles collide and annihilate, they could produce bursts of energy that heat surrounding material unevenly. But what if the inverse is also true? In regions where dark matter is particularly sparse or stagnant, the lack of these interactions might create unnatural cold spots, cosmic dead zones where dust drifts untouched by ambient warmth. Imagine turning off all the heaters in a single room of a bustling house. While the rest of the building stays warm, that one space would grow unnaturally frigid. If dark matter's hidden hand really is at work here, these cold dust patches could be the first visible traces of its absence, like footprints in reverse. Yet not everyone is convinced. Alternative explanations point to exotic dust chemistry. Most interstellar dust grains are silicon or carbon-based, but in metal-poor environments like the pinwheel, they might form looser, fractal structures resembling cosmic snowflakes. These porous particles could have bizarre thermal properties, radiating heat away so efficiently that they self-chill, like interstellar swamp coolers. Laboratory experiments with analogous materials show that certain microscopic structures can indeed cool themselves below their surroundings under specific conditions, a phenomenon known as radiative cooling. If the pinwheel's dust happens to assemble in these rare configurations, it could create localized cold zones without any external cause. Then there's the wild card: magnetic frostbite. The pinwheel's twisted magnetic fields, which we've already seen defy convention, might be playing referee in this thermal anomaly. In areas where magnetic field lines are tightly wound, they could suppress the motion of charged particles, effectively stifling heat transfer. Dust grains trapped in these regions would find themselves isolated from the usual thermal chatter of the interstellar medium, like someone stranded in a soundproof room while a party rages outside. This would explain why the coldest dust often coincides with the most distorted magnetic signatures, a clue that's hard to ignore. Of course, the simplest answer might be that we're misreading the data entirely. Submillimeter telescopes, which detect these cold dust emissions, often struggle to distinguish between truly frigid material and foreground interference from our own galaxy. What looks like a pocket of frost in the pinwheel could be a veil of Milky Way gas faintly superimposed over the image, like breath fogging a window just as you try to peer through. But even after accounting for these artifacts, the chill persists, leaving astronomers with a cosmic detective story where every lead seems to double back on itself. What makes this enigma more than a curiosity is its potential to rewrite two playbooks at once. If dark matter's absence is the cause, it offers a new way to map the invisible scaffolding of the universe. If exotic dust is to blame, it means interstellar chemistry is far more complex than we imagined. And if magnetism or some unknown force is at work, well, that's when the real fun begins. Every icy grain in these anomalous zones is a messenger, quietly testifying to processes we've yet to name, and the pinwheel, ever the cosmic rebel, seems content to let us shiver in uncertainty until we crack the code. The Pinwheel Galaxy may look like a solitary cosmic pinwheel spinning in perfect isolation, but its outermost edges tell a different story, one written in faint, looping rivers of stars. These stellar streams, known as tidal tails, are the ghosts of galactic encounters past, stretched like taffy by gravitational forces so powerful they can wrench stars from their homes and fling them hundreds of thousands of light years into the void. Most galaxies, including our Milky Way, bear scars from such collisions, but the pinwheel's tidal tails are unusually rich with clues, each errant star a breadcrumb leading back to a cataclysm that reshaped this galaxy's destiny. The most prominent tail arcs northwest of the pinwheel's disk, a gossamer chain of red giants and ancient stellar clusters drifting in loose formation. Unlike the galaxy's vibrant spiral arms, these stars move in chaotic, intersecting orbits, like cars merging onto a highway from all directions at once. Their chemical fingerprints betray their origin, higher in metals like iron and magnesium than the pinwheel's native halo stars, suggesting they were stolen from a smaller, denser galaxy that ventured too close. Reconstructing the collision is like piecing together a car crash from skid marks. Computer simulations point to a high-speed encounter, roughly 1 billion years ago, where a dwarf galaxy, perhaps 1/10 the pinwheel's mass, sliced through its outer disk at a steep angle. The intruder wouldn't have survived. The pinwheel's gravity would have shredded it, scattering its stars into looping debris trails while absorbing its gas to fuel new star formation. This would explain the pinwheel's lopsided gas distribution and the sudden burst of stellar births in its northeastern quadrant, echoes of a feast after a cosmic predator devoured its prey. But the real surprise lies in the tail's structure. Instead of fading smoothly like typical tidal debris, some segments knot into clumps, as if the dwarf galaxy's core held together long enough to deposit intact globular clusters along its death spiral. One such knot, dubbed Stream K, glows with the collective light of 1,000,000 suns, its stars so tightly bound they've resisted dispersal for eons. If confirmed as a surviving galactic nucleus, it would mean the pinwheel didn't just absorb a dwarf, it digested a galaxy whole, leaving behind indigestible bits as celestial fossils. The encounter's legacy isn't just in the stars it scattered, but in the chaos it seeded. The collision likely triggered density waves that reinforced the pinwheel's spiral arms, shaping the iconic structure we admire today. It may also have flung the galaxy's central black hole into exile, explaining its mysterious absence, and the stolen gas that's still here, cycling through the pinwheel's star-forming factories, turning the victim's remains into new generations of stars. Yet the most haunting question isn't about the past, it's about the future. Tidal tails aren't static, they orbit their host galaxy like slow-motion comets, and their gravity tugs back. Over billions of years, these ghostly streams could perturb the pinwheel's pristine disk, warping its symmetry or even funneling fresh stars back into the mix. Every star in those tails is a ticking clock, a reminder that in the cosmos, no encounter ever truly ends, it just rewrites the story. And the pinwheel's next chapter might still be hiding in the whispers of those ancient wayward suns. From vanishing black holes to rogue stars hurtling through space at unimaginable speeds, the Pinwheel Galaxy has defied expectations at every turn. We've explored hypervelocity runaways fleeing gravitational crime scenes, phantom spiral arms that vanish and reappear like cosmic ghosts, and gamma-ray whispers with no identifiable source. We've witnessed superstar clusters packing millions of suns into spaces smaller than our solar system, green pea pockets mimicking the early universe, and lopsided gas disks spinning stubbornly out of alignment. Each discovery peels back another layer, revealing a galaxy that doesn't just bend the rules, it rewrites them entirely. What makes these 30 mysteries so extraordinary isn't just their strangeness, but how they intertwine. The missing supermassive black hole might explain the galaxy's turbulent past, while the lopsided hydrogen distribution hints at ancient collisions that left scars in the stellar tide. The overabundance of Wolf-Rayet stars suggests a coming fireworks show of supernova, and the misbehaving Cepheid variables threaten to warp our cosmic yardsticks. Even the cold dust patches and twisted magnetic fields seem to whisper about forces we've yet to name. Together, they paint a portrait of a galaxy that's less a static snapshot and more a living laboratory where the universe conducts experiments we're only beginning to decode. Yet for every answer, a dozen new questions emerge. Could the Pinwheel's phantom bar be a relic of a long-ago merger, or is it quietly reshaping itself before our eyes? Are those hypervelocity stars tracing paths to hidden black holes, or do they hint at gravitational disturbances we've yet to map? And what about the gamma-ray glow? Could it be dark matter's first calling card, or something even more exotic? The beauty of this cosmic puzzle is that it refuses to fit neatly into our textbooks, reminding us that the universe is far weirder, far wilder than we've dared to imagine. So what's next for the Pinwheel? With every advance in technology, from sharper radio telescopes to AI-driven data analysis, we peel back another layer of its secrets. Perhaps the James Webb Space Telescope will spot the missing black hole's shadow, or a new generation of observatories will catch a fast radio burst mid-eruption. Maybe the key to understanding its tilted gas disk lies in simulations we haven't even run yet. One thing's certain, this galaxy isn't done surprising us. Now it's your turn. What fascinates you most about the Pinwheel's enigmas? Do you think the missing black hole is hiding, or was it truly ejected? Could the green pea regions hold clues to the universe's first galaxies? Drop your theories in the comments, because in a cosmos this mysterious, every perspective brings us closer to the truth. And who knows, your idea might just be the missing piece that helps unravel the Pinwheel's greatest secrets. After all, the universe doesn't give up its wonders easily, but that's what makes the hunt so thrilling.